Welcome. This video is going to talk about the process of dissolving, or what scientists call solvation. So why do some things dissolve in each other and other things don't? Well, it all comes down to being attraction between the solute and the solvent. There has to be an attraction between these two substances that's greater than the attraction of the solute to itself. So the solvent surrounds the solute, and if the attraction is great enough, it literally rips it apart or pulls it apart, and this is called solvation. So in my picture here, the green and blue is representing the ionic compound sodium chloride, the green being the chlorine, the blue being the sodium, and then the little red and white thingies are water molecules. And water, as you maybe remember, has a positive end by the hydrogen and a negative end by the oxygen because of its polar bonds or its polarity. And sodium chloride also has positive ions and negative ions. In the second picture, the sodium is the positive white and the chlorine is the negative green ions. And so water comes in and it flips either the positive or the negative end to attract the opposite ion, and it slowly carries off the sodium and the chlorine ions until the salt is evenly spread throughout the solution. So why does it dissolve? It all starts with an attraction. The general rule is like dissolves like, and what chemists mean by that is that polar substances will tend to dissolve other polar substances, while nonpolar things dissolve other nonpolar things. Now, ionic aren't covalent, so they're neither considered polar or nonpolar, but really ionic is a really extreme polar. It's like a superpolar because the electrons have actually been transferred. So polar also dissolves ionic since they both have charges or dipoles. Water is often given the name universal solvent because its high polarity and hydrogen bonds allows water to dissolve ionic and polar things, regardless of how strongly polar, or if it's only slightly or very strongly polar. Water is able to dissolve lots and lots of stuff, which gives it the name universal solvent. So the rate of solvation, how fast it dissolves, you can't change whether something's going to dissolve or not without actually changing the substance, but you can change how quickly it dissolves. And to do that, you have to increase the number of collisions between the solute and the solvent. Because remember, this is all about the solvent getting into the solute and carrying it away, spreading it out equally in the solution. So the three common ways to increase it, you could probably come up with these on your own, because certainly there's been enough times when you've been cooking that you've been trying to get things to dissolve. So you can agitate the solution, and the two easy ways are to stir or shake it. You can heat the solution, or you can increase the surface area of the solute. In other words, you can crush it. If you use finely grained sugar, it dissolves much quicker than coarser grains. So, and of course, if you want to slow down the rate of dissolving, you do just the opposite. You don't agitate it, you cool it down, and you leave the solute in big chunks. The other thing to mention with dissolving is that there's something called the heat of solution, which refers to the overall change in energy, which we notice as a change in temperature in the solution during solvation. There will always be a change in energy or a change in temperature when something dissolves. It can be what we call endothermic, meaning that heat is being absorbed by the solution, so the solution actually feels colder because it's taking heat from the container, the test tube, whatever, the surroundings. And so that feels colder to us as the solution itself absorbs or stores that energy. Or it can be what we call exothermic, meaning heat is released and the solution and the container it's in feels warmer to us. But there will always be a change in heat. It might be slight, but there will always be a heat of solution, either an increase or decrease energy. With solubility comes some terms that we really need to be able to recognize when we're talking about solutions. The first term is the word insoluble, and that simply means doesn't dissolve, just like it sounds. Solubility is the maximum amount of solute that will dissolve in a given amount of solvent at a specified temperature and pressure. So all three of those things affect how much solute can dissolve: the amount of solvent you're trying to dissolve it in, the temperature you're trying to dissolve it in, and the pressure that your solution is at. And solubility is generally expressed in grams per liter. So that's grams of solute in liters of solution. So that almost looks like molarity, except remember molarity is moles per liter. So solubility is a little easier to calculate. You simply find the mass of your solute on the balance, measure out the liter of solvent you're using, and you can calculate solubility. Solubility is often shown on a graph as what we call a solubility curve. And oftentimes it shows the grams of solute dissolved in 100 grams of solvent versus some temperature. And pressure is usually considered to be normal atmospheric pressure around 1 atmosphere. So the factors affecting solubility are the 3 things we just discussed. The amount of solvent, the more solute that can dissolve, quite simply because there's more room. There's more space for that solute to spread out into. The temperature of the solvent, and this is because warmer solvent means more movement. So more movement is going to mean more is able to dissolve because the solvent is going to spread out further and there's more space again. Now gases are just the opposite. When gases are trying to dissolve, they will dissolve more when they're colder because even though the solvent heats up and has more space between its particles, the gas also heats up, and when gases heat up, they tend to get even less dense, or the bubbles rise up and escape even more quickly. So a warm soda will fizz and lose its carbon dioxide much more easily or much more quickly than a cold soda. And then the last one, pressure on the solvent. This really only affects gases since liquids or solids don't easily escape from the solvent. So more pressure on gases means more gas will dissolve because pressure is going to be holding the gas in there. We're talking about the pressure on the solvent, not the pressure of the gas in the solvent. So there's something called Henry's law that you can use to figure out the solubility of a gas under certain pressures. And the law says S1 over P1, so solubility 1 over pressure 1, should be equal to your second solubility over your second pressure. So S, or solubility, again, is measured in grams per liter. So quick example here to show you what I mean by this. It says if 0.85 grams, let me get my marker here, 0.85 grams of a gas at 4 atmospheres of pressure dissolves in 1 liter of water at 25 degrees, how much will dissolve in 5 liters of water at 1 atmosphere of pressure at the same temperature? And if you remember, Henry's law doesn't incorporate temperature because it's assumed temperature is remaining the same. If your temperature is changing, then Henry's law isn't going to work for you. So S1 over P1, S1 is 0.85 grams in 1 liter of water. So I could just put 0.85 grams per 1 liter of water, and the pressure was 4 atmospheres. S2, I've got, I'm being asked how much will dissolve in 5 liters of water. Well, S2 is what I'm trying to figure out. What is the solubility when my pressure goes down to 1 atmosphere? So if I cross multiply and divide here, I find out that S2 is going to be equal to 0.85 grams per liter times 1 atmosphere divided by 4 atmospheres. And when I calculate that, I see that S2 is going to be equal to 0.2125, I'll just round it to 0.21 grams per liter, because my atmospheres cancel out, and remember, solubility is in grams per liter. Now, I'm not quite done because it asked how much will dissolve in 5 liters of water. So if 0.21 grams will dissolve in 1 liter of water, I could just multiply this by 5 liters, and I can expect 1.1 grams or 1.106 grams to dissolve in 5 liters of water. So 1.1 grams would be my final answer. A couple other terms that you should know about with solubility are the terms saturated and unsaturated solutions. So if you think about a a sponge holding all the water it can. You pick the sponge up and it's dripping water. That's saturated. Saturated means it can hold no more. So when solubility reaches the maximum for that temperature and pressure and the amount of solvent, you've dissolved all you can. So when you put sugar in your cereal and all of a sudden the sugar starts sinking to the bottom of the bowl because the milk can't hold any more. An unsaturated solution is any amount you add before it reaches the maximum. So you put a little in, put a little more in, put a little more in. That's unsaturated until all of a sudden no more dissolves and the salt or the sugar starts falling to the bottom of the container. That's unsaturated. It's usually shown with a graph like this. So when we look at this graph, let me point out a couple things here. First of all, I've got 3 different substances. They're all dissolved in water, 100 grams of water, so that's the amount of solvent. Down here on the x-axis, I have the temperature. And again, we're going to assume this is at standard temperature and pressure. So, not standard temperature because the temperature is changing, but standard pressure, 1 atmosphere. And I've got 3 different solvents. And so when I look at this, if I look at 60 degrees, I can see at 60 degrees as I look up, NaCl is going to have the least dissolved, somewhere in the 40s, because 25 is this line and then 50 above it. So, maybe 40, 42. KNO3 is going to have slightly more. It's going to be up in the 80s somewhere. And NaNO3 is actually be over 100 grams, dissolved in 100 grams of water. So the lines themselves, that is the solubility. Okay, that's the maximum amount. That's where saturation occurs. If you put in the amount that the line represents, that is the saturated amount. So then any amount below the line, below the yellow line, below the blue line here, below the green line, that's where it's unsaturated, is when you put in lesser amounts. So what does the line represent for each compound? It represents the saturation or the solubility. What does the area below the line represent? That represents when it's unsaturated. What does the area above the line represent? It can represent 2 things. It either represents excess, okay, that's going to be the excess solute between here and here. That's how much is going to precipitate out or fall to the bottom. Basically, that's what you're wasting. Unless you create something called a supersaturated solution, which we'll look at on the next slide. Which solute has the greatest solubility at 20 degrees? Well, at 20 degrees here, the yellow line is the highest, so that would be NaNO3. At 100 degrees, though, now the blue line has taken over with the greatest solubility. And finally, which solute does temperature have the greatest effect on? It seems to have the greatest effect on KNO3 because from 0 degrees to 100 degrees, KNO3 saw the greatest increase in its solubility, going from less than 25 up to nearly 200 grams. Which solute does it have the least effect on? NaCl. NaCl stayed very close to the same, had very little change from 0 to 100 degrees. The next thing to talk about is this idea of supersaturation. This is when a solvent actually dissolves more solute than it should at that temperature and pressure. Now, a logical question is, then how can that be the maximum if you can dissolve more? Well, it's because you kind of trick the solution into dissolving more. It happens by heating the solution up to a higher temperature and then cooling it back down slowly so it stays dissolved. And this is what you basically are doing when you're making fudge. You're heating it up to get all that sugar to dissolve. You're beating it to keep it dissolved, and then you're going to let it set nice and easy so that it doesn't crystallize, and you get this nice smooth fudge. So things like rock candy, fudge, those things are examples of supersaturated solutions. You also see it the mineral deposits in rocks when you see crystals. That's usually the result of a supersaturation. Or in my classroom with the saltwater tank, you see what's called salt creep, or in the winter around here because we put salt on everything. When you see the salt growing out of a puddle at the end of your driveway in the winter, you can see the salt crystallizing out. That's because it's reached a supersaturation as the water evaporated off.